One of the common problems with very simple square wave oscillators is that they sometimes don't want to start. And then especially when the voltage supply here slowly gives up its voltage and to say the circuit, and that's the typical problem. Anyway, I made in my opinion a useful test oscillator that does not suffer from this problem. And of course it's a big problem when you want to make, say, an oscillator or so, or you want to drive a transistor unit for high voltage or for whatever other purpose. When you, say, switch on the voltage to the circuit and it doesn't want to oscillate. Classical problem, and there are more videos about this issue on my YouTube channel. Anyway, this is a new circuit, in a certain way new, also old, of course. When you go to the 1960s literature in electronics, you will always find these kinds of circuits consisting of one transistor here and one transistor here, and I've used by purpose here now a Darlington, and the good thing of that Darlington is that it has an enormous current amplification, so that helps a lot to make this circuit to oscillate. Given that problem, anyway, the start problem, anyway, here are the pin connections, and I want to demonstrate it now. In my opinion, it is a useful oscillator. You can use it for, say, driving a transistor, driving a high voltage circuit, when, for instance, you use this output here to drive a Darlington within its collector lead, a high voltage transformer, etc., etc. And the good thing is that this circuit can also make needle pulses. The frequency is now 200 Hz up to approximately 5 kilocycles. When you use here smaller value capacitors, and I don't think that you can go, say, lower than 4.7 nanofarad. That is 4,700 picofarad. It could be that you can get to higher frequencies than 5 kilocycles. Anyway. So that was the circuit. Let's try and see what this circuit can bring us. Always important. Here is it on the, say, breadboard. I've used now two switches here. They switch in the capacitor of 470 nanofarad here and 470 nanofarad here, and it means that we now can see, say, the highest frequency of this simple oscillator and the lowest frequency, and here is the waveform. I have to switch off the lights. We are now on, say, 490 Hertz, and you can see it's a kind of needle wave, but anyway. And now turn one of the pot meters in the circuit. I have to put down the camera for a while. So, this is the potentiometer that is mounted in between the base of the BC547B. That is the first transistor. It goes from the base to the collector of the Darlington, and the Darlington was made with a BC547B and a BD139. Turn it now. Let's see what happens. Well, don't have an enormous frequency deviation, but anyway, does not seem bad to me. 986 Hertz. And I turn it back again. 450 Hertz. Well, I've now switched in the two capacitors of the highest value, and they are 470 nanofarad. Now I switch them out, and of course in that case we will see a much higher frequency. This is one switch out. Of course we have now the situation that on one point of the circuit there is that 22 nanofarad cap, and on the other one, on the part of the circuit, there is that 470 nanofarad cap, so a 0.47 microfarad cap. I switched that out also now. So now we are on not the highest frequency, I think. Otherwise I have to do the whole video all over, but anyway, we are on 379 Hertz. Well, this is the higher frequency. Well, and now we are on 3.2 kilohertz. The waveform is quite okay. Now I turn that potmeter, the frequency dependent potmeter, and let's see what happens. 4.48 kilohertz and 3.2 kilohertz. Well, that's more or less everything to tell. You can say change the output level, but that output level changes also a little bit how the waveform looks like. That is in a certain way logical, but anyway, here is the output level changes. No problem with that. And at the end of the second transistor of the Darlington, we have that 470 ohm potentiometer, and that also gives a lot of effect, and especially when you want to realize, say, needle pulses, it helps. Here are quite a few needle pulses in the order of 3.51 kilohertz, and you can use these needle pulses, for instance, to drive high voltage transformer, of course with a Darlington in its primary lead. So I now turn that 470 ohm potmeter, and you can surely see that you can get to needle pulses but also to other pulses. Anyway, 3.2 kilohertz, that's not bad. And perhaps more important to tell is that when you change here the value of this capacitor, so in between 10 nanofarad, that is 10,000 picofarad, and say 1 microfarad, that's an enormous difference, but anyway, when you change here and in this here and here the capacitor values, say 10 nanofarad, 47 nanofarad, and also here 47 nanofarad, and here 47 nanofarad, etc., etc., you can get to different frequencies. So I have in this video only say showed the borders of this oscillator, but even when you go to higher capacitance values, say 1 microfarad here, I did not test that by the way, but anyway, you will go to lower frequencies. That's completely classical radio and electronics theory. Thanks for watching. Let's look somewhat further on the waveforms. I think they are interesting and useful. It's now dark on my workbench and I have to take my screwdriver again. And the good thing of this oscillator is that it always starts, and that's a kind of standard problem. So let me demonstrate that. I switch off now the power supply, and especially these circuits with 2 transistors don't want to start when the supply voltage slowly goes up. So let me demonstrate. Now it goes slowly up, but this one wants to start. Thanks for watching again. Hope it was a little bit interesting. And it was all.